Pleasure to be here. And what I'd like to tell you about today is a little bit of an overview to the field of neutral atom quantum computing, but then the majority of my talk will actually be specifically about the kind of work we do in my lab, which is developing a particular type of neutral atom quantum computer, which is one based on ytterbium atoms. So at a high level, this is kind of basically a picture I like of what a neutral atom computer looks like that encodes the essential elements of it. Not exactly explained along the DiVincenzo criteria, but roughly. So in a neutral atom quantum computer, the heart of it is a vacuum chamber where there's an array of atoms trapped inside, and these atoms form the qubits. So each atom is one qubit, and the qubit might be encoded or is typically encoded in the spin of the atom. And these atoms are held in tightly focused laser beams called optical tweezers. And you can make very large arrays of these laser beams up to tens of thousands using various kinds of optoelectronic technologies that already exist, like spatial light modulators and acousto-optic deflectors, things like that. To learn about the states of these atoms, to measure the qubits, we image fluorescence from the atoms onto a camera that you can use to actually see fluorescence from single atoms. And I'll show you many pictures like that later in the talk. And then to control the qubits, to manipulate them, we also use laser beams that are focused down onto the individual atoms to do both single qubit gates and 2 qubit gates. And finally, neutral atoms don't actually interact strongly with each other. There's no charge, but to make them interact in order to generate entanglement, to do 2 qubit gates, we excite them to very highly excited atomic states called Rydberg states. So those are the basic elements. And in the next few slides, I'll walk you through some of these components in a little more detail. So the first key technology that goes into making a neutral atom quantum computer is what are called optical tweezers, which is the way that we make an array of atomic qubits, neutral atom qubits, and hold them in place. This is now about a 20-year-old technology within atomic physics, and it's actually a very simple kind of laser cooling experiment. So this is a picture from our lab of a vacuum chamber, and that green cloud you can see inside is what's called a magneto-optical trap. It's a laser-cooled cloud. There's about 1 million ytterbium atoms in there, and that green light you're seeing is the fluorescence from the atoms. That's at 556 nanometers. So then to make these optical tweezers, what we do is we put a microscope objective on top of this vacuum chamber, and then we take a laser beam that's detuned away from the resonance from the atoms, and we focus it down through this objective, and that makes this very tight tweezer potential for the atoms. And then we can image fluorescence from the atoms onto a camera so we can see what comes from just that tiny volume where the optical tweezer is. And so going back more than 20 years to this, pioneering the first demonstration of optical tweezers from the group of Philippe Crongier in Paris, what happens when you do this experiment is that you see that the amount of fluorescence on your camera goes back and forth between a low level and a high level. And if you look at sort of what these pictures look like, you see that it's just a single bright spot. So what you're actually watching here is single atoms from this magneto-optical trap coming into this optical tweezer and then leaving again. And it actually turns out the reason they leave most of the time is because a second one comes in and then they kick each other out through a process known as light-assisted collisions. And this is a really fortunate thing that happens in these traps because it means you can deterministically prepare one atom in the tweezer by just, for example, stopping the loading once you already get one atom. You don't have to worry about the possibility that you have 2 or 3. Now, in this example here, the time that the atoms stay in the optical tweezers is not that long. It's only a few seconds and it's limited by the rate at which additional atoms come in. But if you stop this loading process by, for example, getting rid of the magneto-optical trap around the atoms, then you can keep these qubits for basically as long as you want, just limited by the quality of the vacuum in your vacuum chamber. And the current world record is, I think, around 2 hours. So that is how you make these optical tweezers and get atoms in them. But this kind of stochastic loading process where atoms come and go creates a more fundamental problem if you now want to make a large array of, say, hundreds or thousands of qubits, because if you just stop the loading at some particular time, the probability that any given trap is loaded is about 1/2. So the probability that 1,000 traps are simultaneously loaded is 1/2 to the n. That's quite small. But there's an important idea that was demonstrated for the first time now, about 7 or 8 years ago, which is called rearrangement, which is based on the fact that not only do these atoms stay for a long time once you turn off the loading, but you can also take a picture of which sites are filled, and even that arrangement of the atoms will survive the picture. So the idea of rearrangement then is you start out, you initially load your tweezers, and there's some random subset of the sites are loaded, but then you take a picture and the atoms stay where they are, and then you compute in that given shot how you can move the atoms to create an array without defects. So in a one-dimensional system, what you can just do is squeeze out all the empty sites, just compress all the empty sites to move all the atoms to one side. But in 2D, there's also more sophisticated algorithms you can use to pick up individual atoms and move them into the right place. And people have also even done this in 3 dimensions. So this idea of rearrangement now allows you to prepare deterministically arrays of, I think the record is currently maybe 300 or 400 qubits. Okay, so the second key technology that goes into a neutral atom computer is the question of how to make these atoms interact with each other so that you can generate entanglement. If I just have 2 neutral atoms sitting in their ground state, they really do not know anything about each other at all. They don't feel each other's presence at all. And that's actually in some ways beneficial because it means there aren't interactions going on when you don't want there to be interactions. But the way we can turn on interactions to do gates is to excite atoms from the electronic ground state using a laser to a very highly excited state called a Rydberg state. These are states where the principal quantum number maybe goes from n equals 5 to 50 or 100 or something like that. What is interesting about these states is that when you go to these very high-lying states, the electron orbit around the atom gets very big. It actually grows as the square of that principal quantum number n. So if the ground state of, say, a rubidium atom, which has n equals 5, looked like this, a Rydberg atom with n equals 50 would be, this much bigger, and n equals 100 would be even 4 times bigger again. So these electron wave functions can get almost to be micron sized. And then correspondingly, these very large and fluffy electron clouds are very polarizable. This polarizability actually grows as the 6th or 7th power of the quantum number. So what that means is the van der Waals interaction between 2 of these, which is related to polarizability, grows even faster. This actually grows as the 11th power of the principal quantum. So what this the fact that you have this interaction that grows extremely rapidly with n means that even though you have very small interactions in low principal quantum number states, you can switch on extremely strong interactions to do very fast entanglement and then come back down to turn off the interactions when you're done. There's many different ways to use this interaction to generate entanglement, but the most common approach is something called the Rydberg blockade. And the idea of the Rydberg blockade is as follows. So if I have one atom by itself and it's just got a ground state and then some highly excited state called a Rydberg state, and I'm coupling between them with a laser, I could, drive Rabi oscillation, say, on this transition all day long. But if I now put this atom near another one that's already in the Rydberg state, the van der Waals interaction between them shifts or basically increases the energy cost to excite the second atom into the Rydberg state. And if the amount by which it shifts this state, U, is larger than the laser Rabi frequency omega, then this excitation is blocked or blockaded. You can't do it. So this is how the state of one atom, whether it's in the ground or the Rydberg state, can control the excitation of the second one. And the thing that's nice about the Rydberg blockade as an interaction mechanism is that it doesn't actually depend on what the precise value of this U is, so long as it's very large compared to the laser Rabi frequency. Right. So the way we always summarize the Rydberg blockade is that there's a characteristic radius, the blockade radius, and you just cannot excite 2 atoms to the Rydberg state simultaneously within that radius. For typical atomic parameters and laser parameters, this blockade radius tends to be between 5, 10, maybe 15 microns, which it works quite well with optical tweezer technology, where we can typically make tweezers with spacings of 2 or 3 or 4 microns. So the fact that this blockade radius is a couple of sites, but not infinitely many sites, is a really ideal scale. And then the last ingredient is that, on that last slide, I showed you sort of a 2-level atom that has a ground state and a Rydberg state. But if you really would like to encode a qubit for a long time, you'd like to actually use multiple ground states that are stable that might correspond to different configurations of the electron or the nuclear spin. And you can also use qubits like that and entangle them through the Rydberg state if you have the ability to selectively excite only one of the 2 qubit states to the Rydberg state, which you can get by just tuning your laser to a particular frequency. So you can only excite one of them. So it's a little more intricate to understand how you do actually gates in this case, but the basic gist of it is that if I have, say, a pair of qubits and only one of the state 1 goes to the Rydberg state, if only one of them is in the 1 state, then the dynamics of the excitation of the Rydberg state is not affected by the fact that there's 2 qubits. But if I have both of them in the 1 state, then the blockade kicks in, only one of them can go to the Rydberg state. That gives you some different excitation dynamics that you can turn into a 2-qubit gate in various ways. And so the current record fidelity for 2-qubit gates is actually, it was 98% for a while, and it's now, in the last couple of months, 99.5%. From Misha Lukin, Vladimir Vuletich, and Marcus Greiner's experiments at Harvard and MIT, which is now basically in the mix of what the state of the art is for any other qubit platform. So I don't want to read too much into what David DiVincenzo said in his last talk, but I think it's this kind of line of experiments here that have maybe showed that this is now a very compelling technology for quantum computing.
And if there are a couple of questions
sure.
to repeat a little bit. Varda asks, how do you keep the atoms in such a high excited state, and why does the blockade actually take place? Could you review again?
Well, so they don't stay in the excited state for very long. We basically put them up there with a laser, and then we bring them back down when we're done. And we don't want to leave them up there for too long because they have some probability to decay on their own, and that would be an error in the gate. So we basically like to get in and out of that state as fast as possible.
Can you share more? What's polar? Oh yeah, go on.
Well, what is the blockade? So, I mean, okay, I think it's maybe something you learned from chemistry class, that the van der Waals interaction, which is sort of just generically responsible for why things stick to other things, comes from polarizability. That basically, if you have many objects tend to lower their energies in an electric field. And so when you put two polarizable objects near each other, they want to stick together and you get this 1 over the R6 interaction. That's basically the same thing that's going on with these Rydberg atoms. So by making the electrons so big, you make them very polarizable so that they respond very strongly to electric fields. And when you put them near each other, they respond very strongly to each other's electric fields.
Great. And with that, you also answered what polarizability is, and we are ready to continue.
Yeah, so there have been a couple of, so it's an exciting time for neutral atom quantum computing, and there have been breakthroughs in gate fidelities just in the last year, but also in other really important ingredients for quantum computing, like being able to do, mid-circuit measurement, measure some of the qubits in the middle of a circuit, which is important for error correction. And also the Lucan collaboration at Harvard and Mark Saffman's group at the University of Madison, or Wisconsin-Madison, have also demonstrated in the last year the first, what I would call like programmable quantum circuits, where they have many qubits and they can specify a sequence of gate operations and run them. So all of this just in the last year or two, makes it a really exciting time for neutral atom quantum computing. So I'm going to switch gears now and tell you about the work that we do in my group and where that comes into the field. And so where we started, with our experiments about, 6 years ago at this point, so everything I showed you up to this point was done with the alkali atoms. These are atoms that are hydrogen-like. They have just one valence electron, and they have a very simple level structure. But a few years ago, we started looking at the next most complicated atoms on the periodic table, which are these alkaline earth atoms. These have 2 valence electrons. They're basically like helium. And some of the widely studied ones are strontium and terbium. Even though terbium is down here, it has the same electronic structure as its friends over here. And these atoms have some interesting properties that make them useful for lots of things. So the difference in the level structure of these that you get from having 2 electrons is that you have now both those 2 electrons can have their spins anti-aligned, in which case the total electron spin is 0. Those are called singlet states, or they can have their spins aligned, and that makes a triplet state. And transitions between singlet and triplet states are forbidden, which means they happen much less frequently. So that gives you generically 2 different kinds of optical transitions, ones that are like allowed between, say, singlet states or between triplet states, and ones that are between singlets and triplets, which are narrow and forbidden. And this turns out to be really advantageous for laser cooling, because these broad transitions let you cool fast to get from room temperature down to low temperatures, but these narrow transitions let you cool to extremely low temperatures, because the fundamental limit of how cold you can get an atom, called the Doppler temperature, is actually related to the line width of the transition. The second thing that's really nice about these atoms is that in the ground state, when the 2 electrons are sort of anti-aligned to each other, so there's no electronic spin, if you have an isotope that has a nuclear spin, that nuclear spin doesn't couple to anything. It just is very isolated. So it actually makes essentially the best qubit you could imagine, because it has very little sensitivity to magnetic fields or to optical fields. The third thing that's interesting about these atoms is, well, this is the true ground state is a singlet state. There's also the lowest energy triplet state also has a very long lifetime, even though it's not technically stable. In a terbium, this state has a lifetime of a few tens of seconds. And it also still has no net electronic spin, so you can also put a qubit here. And this is actually what I'll talk about in this talk, is explaining why it is that you actually want to do this into what we call this metastable triplet state. And then the last thing that we won't get into too much, but is that it turns out that once you go to these Rydberg states and these alkaline earth atoms, you now have a trapped ion inside the Rydberg state, because when you take these 2 valence electrons and you put one of them in the Rydberg state, you're now left with 1 valence electron inside. This looks like an alkali atom. And you can use the optical transitions of that ion inside the Rydberg atom to do a lot of interesting. So I don't claim to have explained all of these things in detail, exactly why you should care about them, but the actual picture I want to leave you with is that this slightly more complicated level structure is a little bit like a Swiss Army knife. So, when we started working on this a few years ago, we knew that there were lots of interesting and weird features in here. We didn't actually know what they were all going to be good for, but kind of in a somewhat literal sense, our research program over the last 5 years has been just opening this Swiss Army knife, pulling out various tools and seeing if we can find something useful to do with it. Okay, so with that, there's two main things that I want to tell you about from our own research in this talk. The first is about a new kind of neutral atom qubit that we recently demonstrated, which is based on this metastable state in ytterbium. But before I can tell you about that, I want to explain why it is that we're interested in this kind of qubit. And it is based on a theoretical idea that we developed a few years ago in collaboration with Shruti Puri at Yale and Shimon Kolkwitz, which is a new idea for how to do quantum error correction efficiently using an approach called erasure conversion. So in my remaining time, I'll probably spend roughly equal time on these two. So in a quantum computation, the fact that errors can occur is basically the main obstacle right now. If we had perfect qubits where you could do perfect gates, I am sure we would be factoring large numbers and things like that already. But the fact that qubits have decoherence, gates have errors, is the problem now, no matter how you look at it. Fortunately, there's still a path to doing quantum computing, and what that's based on is quantum error correction. And quantum error correction is essentially the idea that you can take the information that you're trying to compute on and encode it redundantly into not just one qubit, but several qubits, so that if an error happens to one of them, you can use the remaining information in the others to recover the state that you care about. Error correction is also a well-developed idea in classical computing and communication. And to give you just the simplest example of a classical, by which I mean not quantum, error correcting code, let's consider that I have a channel where I can just send bits of information to somebody that I want to talk to, but it's noisy, so they don't hear some of the bits the right way. So if I want to actually send the information 0, then what I could do, instead of just sending 1 0, I could send 3 zeros. So redundantly encoding it. And if I want to send 1, I could send 3 1s. And then the receiver, the person who's listening on the other side, will use a very simple algorithm called majority vote to decide what message I intended to send. So if I sent 0 0 0, for example, and the middle bit got flipped to a 1, they will still understand that I meant to send 0 because they say, well, there were 2 zeros and 1 1. So it's most likely that they sent 0. However, it is also possible that I tried to send 1 1 1 and then had 2 errors. And if they get this message, they will still conclude that I intended to send 0, even though I actually meant to send 1. So this is a mistake. So this error correction isn't perfect, but it can recover from any single error that occurs in the channel. So there is a quantum version of this too, which at a glance is sort of an obvious generalization that if I want to send a quantum state, alpha 0 plus beta 1, there's a superposition of 0 and 1, then I would again use this redundant encoding to send alpha 0 0 0 plus beta 1 1 1. But there's a problem now, which is that if the receiver wants to do the majority vote kind of operation that we described previously, it seems like they would have to look at the qubits to ask, well, are they the same or not? And if they just go and measure the qubits directly to figure out, whether there's more zeros than ones, they're actually going to collapse this superposition and destroy the quantum state that we were trying to transmit in the first place. But a really important idea from Peter Shor is to instead to still look at the system, but to be very careful about how you measure the qubits. And instead of just measuring the qubits, you just ask exactly the question you want to know the answer to, which in this case is about the relative parity of 2 qubits. So for this code here, I can learn about whether any of the individual bits have errors by asking 2 special questions. The first is, are qubits 1 and 2 the same as each other? And the second is, are qubits 2 and 3 the same as each other? And I can do those checks using some extra helper qubits called ancillas and gates like this. And in basically this circuit here, I'm going to flip this ancilla, depending on the state of these 2 qubits, and flip this one depending on the state of these 2. And in the end, by measuring these 2 ancilla qubits here, I learn from the measurement of this one if the first 2 qubits are the same. And from this one, I learn if the second 2 qubits are the same. But importantly, I never learn whether any of these qubits are 1 or 0. So this allows me to tell where errors have occurred without actually destroying the superposition. This particular code can actually only correct bit flips where a 0 becomes a 1 and a 1 becomes a 0, but not the other kind of quantum error that can occur that's a phase flip, where like say 0 plus 1 becomes 0 minus 1, but there are generalizations of this that can also handle it. So a really important idea in error correction is the notion of a threshold, which is related to how many errors you can correct. So I argued earlier that for this kind of repetition code, classically where I encode 1 bit in 3, I can correct one error, but it fails if I have 2 or 3 errors. So I can actually overcome that by using more copies instead, right? So instead of using 3 copies, I can use 5 or 9 or 4,000. And then it turns out if I use D copies, I can correct basically D over 2 errors, which is intuitively makes sense given that it's majority vote. However, this isn't totally for free, because when I use more copies to encode my message, I also create more places for errors to occur in the first place. So even though I can use an arbitrarily large code to correct an arbitrarily large number of errors, that doesn't mean I can always transmit information. It turns out and the way we think about that is that there's actually a threshold error rate. So if the error rate of the channel is below some threshold, then I can use essentially arbitrarily large redundant encoding to get whatever high fidelity transmission I want. But if the error rate of the channel is above that threshold, then by using redundancy, I'm just creating more places for errors to occur, and more errors are occurring, so I don't win at all. And so the way we usually think about thresholds is we plot what's called the logical error probability, or the probability that the receiver gets the correct state as a function of the probability that each bit has an error. And I've shown this here for different distance codes, different amounts of redundancy. And so here the threshold is at 1/2. It's where all these lines cross. And what you see is below the threshold, increasing the distance makes things better. Above the threshold, increasing the distance makes things worse. So error correction only works if you're below some threshold, right? And then the other important point is that even when you are below the threshold, so you need to be below the threshold. Once you are below the threshold, the only thing that matters actually is the ratio of your error rate to the threshold. So your errors are sort of exponentially suppressed with distance if you're below the threshold, and what matters is how far below the threshold you are. Okay, so this threshold property can be extended to quantum circuits too. It's a little bit harder to analyze in that case, because in quantum circuits, the relevant errors are actually almost always occurring during the gates themselves, not just in qubits that are stored. And the reason that's more complicated is now when you use, if you want to analyze the performance of a code, you have to consider, not only correcting errors that occur on qubits coming in, but also errors that are induced during this checking process with these ancilla qubits. And now this actually increases the cost of redundancy, because now if I use a larger code with more qubits, not only do I have more qubits that have more errors, but I also have more gates where errors can occur. So unfortunately, it actually turns out for quantum computing that the best threshold that we know of for sort of a generic error model is from this code called the surface code, and that threshold is about 1%. And so this 1%, it's a lot lower than the 50% I showed you on the previous slide, but on the other hand, it's about where a lot of qubit platforms are right now. So, but still, you'd like to be very far below the threshold. So one area of research now in quantum computing and quantum error correction is to try to figure out how to raise these thresholds. And it could be, we don't know that it won't be the case, that somebody will come up with a better error correcting code that just allows you to have a much higher threshold under sort of generic noise assumptions. But the fact that nobody has improved on the surface code in, I don't know, probably 15 years or so at this point, suggests that maybe that's not the case. However, there is another approach, which is to cheat. And the way you would cheat is by basically trying to design qubits that don't have all possible kinds of errors with equal probability, but where you can suppress some of the errors a lot, maybe intrinsically in the design of the qubit. And if you have a restricted kind of error model that can occur, then that can allow you to raise the. So one example that's been widely studied in the last sort of 4 or 5 years and has inspired the design of a lot of new qubits is something called bias noise, where, say now, bit flips occur more often than phase flips, for example, or vice versa. And so this is stimulated. And so in this case, it's kind of known that you can get thresholds for the surface code and its friends maybe into the, as high as 5 or 6%. And this is motivated sort of specifically by what are called Kerr-Cat qubits, which is a type of superconducting qubit. And also it's motivated people to think about different ways to encode qubits into neutral atoms and ions and things like that. But it actually turns out to be a little bit hard to get this bias noise to work at a circuit level, because you need sort of special gates that don't convert bit flips into phase flips, and that is not always possible. So there's another, so where we kind of got started with our work was to kind of think about a different kind of special noise model that you could have in qubits. And that noise model is to have qubits where most of the errors are what are called erasure errors. So the errors that I showed you before were in a quantum context, we call depolarizing errors. You have bit flips or phase flips. But what an erasure error is an error where when it occurs on some qubit, you know that qubit has had an error. Like the qubit has an error and then it lights up. or something like that. And you have that information about which qubits went bad. And even classically, we can understand why these errors are easier to correct. Okay, if I'm doing majority vote on this repetition code here, it's clear that if more than half of the qubits have had errors, then my majority vote is going to get to the wrong answer. But if instead I know which qubits have had errors, I can exclude them from the vote. And and you can see in this example that even if I have 2 of my bits that have had errors, I can still get to the right state because I just look at the one that didn't have an error. And actually, even if all 3 of them had an error, I can still tell that there's an error. So I'm like never wrong, but I can correct a much larger number of errors. And it turns out if I generalize this to a distance D code, instead of being able to correct D over 2 errors, roughly, I can correct D minus 1 errors. So for this, the advantage here really grows as you go to larger numbers of qubits. And this actually fact that you can correct twice as many errors is a property not just of twice as many erasure errors as depolarizing errors is a property not just of this example, but of any quantum or classical code. It's almost true by definition. And so this helps a lot in terms of the thresholds. Classically, the threshold actually, if you just have these erasure errors, is basically 1 because you don't pay any cost. If you use a larger and larger redundancy, you just increase the odds that one of your bits gets transmitted without having an error. So together with my collaborators, Shruti and Shimon, we kind of thought that this was a neat error model and what would it look like to have a qubit that had these kinds of errors. So then we started looking at our neutral atom qubits, where we have the qubits stored in the 2 spin sublevels of the ground state. And in these kind of neutral atom qubits, by far the dominant error that we have to deal with comes from going to these Rydberg states during the 2-qubit gate. Because when we go to the Rydberg state during a 2-qubit gate, we have to stay up there for enough time for the gate to happen. But this state doesn't have an infinite lifetime. It has some probability of decaying while we're up there. And so those decays are actually the dominant gate errors, the ones that you fundamentally can't get around. So if you just had these 2 ground states and this Rydberg state, when you decayed, you would come back down to one of the 2 qubit levels, and that would be a depolarizing error. But what we realized is that if we use instead this metastable state in a terbium, then these decays actually overwhelmingly go either to the real ground state, where we can detect them immediately by just trying to get the atom to scatter fluorescence, to scatter photons, emit light on some transition out of the ground state, or they get trapped in other Rydberg states where we can also see them at the end of the gate by basically blowing up any of the atoms left in Rydberg states, converting them into ions, and then detecting fluorescence from those ions or doing something else. And it turns out if you go through the branching ratios here, that only 2% of the time that you decay from this state during a gate do you actually come back to the qubit subspace and stay there, which means that 98% of the errors that occur in these gates are detected and thereby converted into these erasure errors that are much more favorable. So with that idea, that erasure errors would be better, and here's a specific implementation for how to do this with atomic qubits, we then asked ourselves, well, how much would this actually help? How would this work? So my collaborator Shruti and her students simulated how this slight variant of this surface code called the XEZX surface code would work with this error model where 98% of the errors are erasures. The way in which they kind of envisioned this in the simulation is that this is a parity check circuit that's used in the surface code. It's a little bit more complicated than the one I showed you earlier. But after every 2-qubit gate, which is where the errors can occur, you check to see if any of these atoms have decayed outside of the qubit subspace. And if they have, you see that fluorescence that converts it into an erasure error. And then, because you blew up that qubit, you replace it with a new one. So in this model, what they found is that the threshold increases from the typical surface code value of around 0.9% to 4.1% if we let 98% of these errors be erasure errors. So this is a very significant increase, a 4-fold increase in the threshold. And what you can see is that this gives you, first of all, makes it much easier to get below the threshold, but also dramatically reduces your logical error rate in some cases by 5 or 6 orders of magnitude, even when you're far below the threshold. So this can make error correction a lot easier and can make it a lot more effective. So that's essentially the idea. And then once we had this idea and worked it out, we then set about trying to do this in the lab. And so that's the next thing I'll talk about, but I can pause now for a second if there's any questions that have come up about kind of the fundamentals of error correction.